Hello, Dr. Fizz here, aka Professor Michael Reese, and I taught at UNC Asheville for over 4 decades. I'm putting together a course here on calculus that is basically a review course for those that had calculus before and maybe it's been a long time. And I want to review the basic calculus that you need in courses in physics and engineering. Now, this course is also being put together for ambitious high school students that want to get an idea of what calculus is before they take a calculus course, for example, in college. Now, this course is no replacement for a calculus course in college. Folks majoring in physics and engineering and the physical sciences should take calculus with a mathematician. That's very important because mathematicians are very precise, and when they talk about limits and the various proofs of things in calculus, this is very important. Here I'm going to summarize the basics, essentials that you need for physics. So in other words, this course complements the courses in college. It's easy to get lost in all the detail when a mathematician is doing an excellent job covering all those topics with limits and being very careful with things. Here in physics, we basically are going to use certain principles of calculus, and that's what I want to review here. So this will serve 2 purposes: for high school students that want to get a jump and understand what calculus is at a basic level, and also for those that want to review some calculus that will be helpful in taking my courses. Now, my courses typically on the Dr. Fizz YouTube channel requires a whole year of calculus-based physics and 3 courses in calculus, except for my introductory physics with calculus. That one would not require that much. That one requires calculus 1 and calculus 2 concurrently. So I hope you enjoy these concepts where we isolate the essential, the basics that we need for applying principles of calculus in physics, engineering, and the physical sciences in general. Chapter O, the topics. Now, the essential idea of calculus is broken down into 2 parts. There's differential calculus and integral calculus. The first part of our course, or a little more than half, will be on differential calculus, and then the second part will be on integral calculus. Now, to understand differential calculus, I want you to think of someone hiking up a trail. Now, we're going up this trail, and we have 2 questions we can ask. 2 basic questions. One is, how high are we? So let's say that the ground level, sea level, is down here. Then your height, let's say the height of the trail, would be this vertical distance. And we could put, say, an axis here, call that y, call this x, and then the various altitudes are your y values, and we often write that as f of x. You put in the x value, that's your distance away from some reference point here where x is 0. And then the graph or the function gives you the height. Now, the subject of differential calculus is for us to calculate what the slope is at each point, and that's useful for a hiker. What's the steepness? Here's a nice little picture sketched by artificial intelligence for me, so I don't have to worry about copyright. And here we're going to be looking at the concept of the slope. Now the slope, how steep things are, what we can do is we can come over here and make a little triangle that approximates the slope here. And this would be the rise, how much we go up, and this is the run. So we're interested in, for the slope, the basic concept of slope is what is your rise as you run out to the right. All right, so the run is your horizontal distance, and your rise is your change in elevation, and that's the slope. I'm going to give you here an example with numbers. And these numbers along the x, 0, 1, 2, 3, 4, 5 to 20, it could represent meters, but for now let's just keep it some distance units. And then these are distance units of elevation. Now the slope, going from 0 to 8 along the x, that slope's the same. So we went up 4 and we went out 8. So that means the rise is 4 and the run is 8. So the slope here would be 4 over 8, which would be 1/2. Now the slope here is flat. There is no rise, so the slope is 0. And then here I simply drew one with the same, let's say the same slope, negative, going down. In other words, this is like in reverse. So here, instead of going up 4, we go down 4. So the slope would be minus 1/2 because we went down 4, negative 4, and we went to the right by 8 because you went from here 12 to 20, that's 8. So this is the first part of our course, figuring this out, where the graphs have curves. They're not straight lines because the straight line is easy. So the calculus is doing all kinds of slopes. So calculus is doing all kinds of slopes like this. But these curves will be have nice mathematical forms, like upside down parabolas and things that we'll be working with, all kinds of functions. So the functions that you learn in algebra, we'll be looking at them one by one and finding their slopes. Now here I have the result of finding the slope of this one up here. The slope is here 1/2, so I put 1/2 here. Now this scale is different than that scale, don't worry about that. It's like in a large scale here. So that's 1/2, and also the slope has a different meaning than elevation, so it's something else, so don't worry about the scale being different here. So this is 1/2, and then the slope is 0, and then the slope is negative 1/2. All right, so this is a 1/2 up here, 0, and negative 1/2. Now I want to show you what integral calculus is, and it's going the other way. Suppose we had the slope information and we wanted to find the elevation. Well, you would go the other way, and that's what we're going to be showing you how to do that. But I want to point out one thing here that's very interesting. If you look at the area of the slope function, we call this the slope function or the slope information, and we designate that with a y prime or f prime of x. Notice that the area here, if you take 1/2 times 8, you get 4, which is where you are right here. This is 4. In fact, as you go out here, bit by bit, you actually climb up here. So if you had stopped, say, in the middle here, then the area would be 1/2 times 4. The area would be 2 here. And then if you stop there, you're at 2. You're at 2 here. That's wild. And this is now going another 2. We broke it down into 2 sections. And then this next section here, you go up another 2 to get to 4. Here, the slope is 0, and there's no area, so you stay where you are. And then here, there's negative area. So then you have this climbing in reverse, and you come back down. In other words, to get the elevation function here from the slope function, you figure out area. And that's our whole course now. That's it. First half of the course, finding the slope. Second half of the course, finding the elevation from the slope. Now notice though, that when you go back this way, you can simply, if this is sea level, you can simply imagine this being higher up. And if it's higher up, if this hill were raised up a little bit, say like this, but the slope happened to be the same, the slope function would have the same result because the slope is the same here at each point. However, the elevation is different. So if we had the slope function for each of these, they'd be the same. But if you want to go backward from the slope to the elevation, when you do that, you have to add an overall constant c, because that takes care of the different elevations that you could have. So taking the slope of the function is a unique thing, but going the other way to find the elevation, well, you can get 2 elevations that have the same slope. So we need to put in a constant going back the other way. And then you find that constant in a physics example or an engineering example. You find that from the application. Maybe your trail began not at sea level, but a little higher up, and then had the same slope as another one that would have begun at sea level. And you just adjust that. So they're the essential concepts of our course, both differential calculus and integral calculus. And now as an assignment for you. So a neat challenge is to try to explain what calculus is without math to a friend or a family member. I remember in high school when a girlfriend of mine asked me what calculus was, and I couldn't tell her. I didn't know. I didn't take calculus in high school. I had to wait until college, and at the time I had no idea. So here you have a basic idea in this chapter, and see if you can explain the basic concept of being on a trail, going up a hill, and that would be something that you could focus on your altitude, like how high are you? And the altitude, you could do a graph leaving home as you go certain distance in a direction. Where are you? Where's your elevation? Now, differential calculus is to calculate the slope at each point, which is nice to know for hiking. What is the elevation and what is the slope, the steepness, which will give an idea of how difficult the hike will be. Then for integral calculus, we want to go the other way. We want to have the slope calculate the elevation. So with differential calculus, you're given this altitude, you're given the elevation, but you have to figure out the slope at each point. That's differential calculus. Then in integral calculus, you're given the slope at each point, and you need to go backwards. You need to find the elevation at each point. So that's basically it, in a nutshell, the basic ideas of calculus, differential, and integral.